This is the 24th Flow Seminar, and my name is Samuel Horvat, and together with Peter Richtari, Virginia Smith, Aurelien Bellat, and Dana Lister, we are the organizers of Flow Seminar. For those of you who are attending for the first time, Flow Seminar stands for Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of the latest scientific research in all aspects of federated learning. This includes, but is not limited just to theory and application in areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization systems, hardware, and many more. For today's talk, it's my great pleasure to introduce you our speaker, Nicholas Lane. So Nick is a senior lecturer in the Department of Computer Science and Technology at the University of Cambridge, where he leads the Machine Learning Systems Lab. He's also affiliated with Samsung AI Center in Cambridge, where he's a director leading research in on-device and distributed machine learning. And I have the honor to be right now interning at his group at Samsung. And today he's going to talk about his work on Flower, which is a friendly federated learning research framework. So Nick, stage is yours.
Oh, great. Thanks very much for the introduction. It's really a pleasure to be giving this talk today. And essentially, before I begin, I want to acknowledge that the work that I'll be talking about today is really the product of a lot of hard work by the folks you see at the bottom of this slide. So my group traditionally has looked into a lot of issues to do with inference-centric efficiency, particularly when it is targeted to mobile and embedded devices. But in the last, I guess, 9 months, we started to look towards how can we start to train these models, not just use them once they're trained, and how would you start to train these models through distributed federated resources of largely constrained devices. And so as we started to look at this area, we produced the software tool Flower that I'll be focusing a lot today. And then as a byproduct of building this tool, we've also started to look at what we think is a really interesting question, and namely, as federated learning becomes more prolifically used, what are the types of carbon footprint issues that we might envision happening? And so that's really the thrust of this talk. Right. So if I move on to this second slide here, the talk really is one of two halves. So first I want to use Flower. I want to illustrate some of the motivations for why we built it and some of the early experiments we've run using it that I think can shed light into some of the more system-related efficiency issues that are associated with building federated systems. And then I think there is a very lovely case study of using this framework that I can work through towards the end. This is all, but in both situations, all very early work. And so I thought it was a useful thing to bring to this community to get feedback and on these early pieces of work and evaluations we've done so far. So let me begin with Flower. And if you're interested in any of the details today, please have a look at the paper or do visit the website. As I'll be elaborating on, it really is it's a framework for doing various kinds of federated learning experiments that traditionally have been far harder to do than we would really want. And so this piece of work really is trying to emphasize people to use the tool, to experiment the tool. And so if you go to the website flower.dev, you'll find a lot of support material for the tools I'm talking about, examples and so on, because we really would like to start to build a bit of a community around it where it can help people perform sort of experiments that they're not able to do conventionally. So let's move now into some of the motivations for us to look at some of the motivations that led us to design Flower. And essentially, when we started to look into this area, we realized that while federated learning has made great strides in the past few years, there's been the establishment of some really interesting algorithms. There are already large-scale systems, such as those run by Google, that are globally using federated learning ideas on a daily basis to millions of people. But something that we thought was an area where the community lacked was in the way that it evaluated its algorithms, and in particular, the way that evaluations were done from a systems perspective. In many cases, the papers out there were designing algorithms and then evaluating them either with a small number of clients, or when they did scale those clients up, they might the evaluation routine, if you could see it, might look something like this, where you had individual clients being sort of very coarsely approximated, even just as elements within a loop. And so when you evaluate a federated learning system in that way, there's a great deal, obviously, of system details that fall off the wagon in your evaluation. So if we bring up just some of the issues that would not be well represented through evaluation styles of this type, there are obviously networking and wireless fluctuations that are very complicated to model. They're never going to be captured if you just have your clients acting as elements in an array, or even just have simple wide connections between different devices. There are examples of compute heterogeneity that are never going to be present, where you might want to federate a variety of devices together. Obviously, memory, energy, and scaling are not going to be captured well. And so if you just think back to some of the underlying motivations for building federated learning systems, such as being able to potentially have robots learn their perceptual model in situ based on what they're seeing, or have devices being able to train things like keyboard models and so on collectively rather than centrally. In these example systems, one would expect to see an awful lot of real-world system attributes, heterogeneity between different types of devices that are collaborating, where you might have a very low-powered device, such as an embedded camera, wanting to also participate in a larger network for example, flagship smartphones, that both of which might have interesting pieces of imagery data that they want to train a model from. And none of these types of issues are going to be sufficiently captured with the types of evaluation strategies that we saw being used in the literature. And so that was one big reason for us to start to look at building something different. The other issue is, even if you put to one side the issue of heterogeneity in its many forms as it can manifest in a large-scale distributed system, there's also the issue of scale. And so we looked around to see some of the recent 100 papers that were being published in top-tier venues in the last few years. And through we did some simple analysis and built this histogram. And so this is federated learning papers. If you go to one of the archive papers I point to, there's an appendix. We came up with a system by which we searched through Google Scholar and through a set of criteria, selected those papers, and then we want to build a histogram to answer the question, well, how many clients are people typically using when they evaluate their algorithms? And what you find is what you see here, that there is a majority of those works are being evaluated at 100 clients or less. And there's very few examples of folks who are evaluating at levels beyond 100. And if you look at those people who are evaluating above 100, you typically see only a small number of commercial players exploring this, exploring that part of the design space. And so this further motivated us to try to look at ways that we could build tools that would allow folks to not only when it's time to evaluate their various types of federated learning methods, their algorithms, their different types of components that fit within these systems, we wanted to provide them a way that they could really scale up their evaluations as well. So we could start to kind of migrate away from testing our designs at what a small number of clients, especially when you think of the motivating scenarios that we want to eventually migrate these techniques to, are often discussing systems on the order of, so 10,000, or maybe even federating over 1 million different devices worldwide. That's our grand ambitions, right? So if we're not evaluating in those types of design spaces, we're going to miss out on a lot of important factors in their performance that are otherwise hidden. And so for that reason, we built this system called Flower. I'm now going to sort of discuss the various sort of components within Flowers to give you sort of a qualitative feel of the types of things that is able to provide somebody who's designing and doing research in this space. I guess I also wanted to mention though that in looking at this area, it's not that it's that we thought people were not evaluating in these different conditions because of that they were just too difficult to do. If you want to, for example, experiment with even say a modest side, let's say 100 different clients, where those federated learning clients have quite a bit of compute heterogeneity within them, well, then you're going to have to write an awful lot of code that can allow these different clients to participate together, to connect, to exchange data. And essentially, there's a lot of different components you're going to have to build up before you even get to the part where you get to do federated learning research. So the more that we could fill that gap for folks and to simplify their pain, we believe that would be a sort of a forcing function that would open doors to folks evaluating in much more realistic settings. So let me sort of walk through the different parts of the design of the framework. The way to think of this framework is that it sits on top of existing deep learning frameworks such as PyTorch, TensorFlow, and similar. It sits on top of those existing frameworks and can in fact incorporate any training loop that you happen to have written in those frameworks already. So we want to make it very easy for somebody who has gone through the effort of building a centralized training loop with all their variety of different types of components to easily integrate it within an umbrella system that would allow them to federate under fairly realistic settings, potentially between devices, even running different frameworks. So that was one motivating sort of umbrella mental model we wanted to maintain with this tool. So if I move from piece to piece, I just mentioned how this umbrella federated learning tool is able to accept training pipelines of various kinds, fit into different types of frameworks. And similarly to promote people to have their clients be from a device, a diverse set of different types. We also have sort of a rich set of SDKs that people can write different clients to run on different types of systems. So we want to make it relatively simple for somebody to have even a bespoke system out there, some sort of exotic embedded system. As long as they can write in a sort of a well-known language like C++, they can write a client that can do the inference and backward passes and so on required for it to participate within the framework. And of course, there is sort of communication clients that also need to be developed to exchange the gradients and so on. Also within this framework, we wanted to make it easy for people to compare against well-known algorithms. And so already in the framework, we've implemented a series of course, well-known federated learning algorithms of different kinds. So folks could quickly implement their particular idea within this framework, get up and running and promote more systematic comparisons between existing algorithms under the exact same system configuration. We felt that was an important aspect too. And alongside these existing implementations of algorithms, we also wanted to give within this holistic framework a series of data sets where you can have existing well-known data sets ranging from, say, CIFAR 10 to different types of audio and speech recognition data sets. So a wide variety of data sets that have existing pre-partitions. So people using this framework can select repeatedly the same different types of data sets, be them completely essentially, or when they're being partitioned to different under different assumptions. And so then this would also facilitate more comparisons between them. And then finally, let me just talk a little bit about the components that we've added to make it easy to address many of the issues I've raised on the right here. So things like, how are you going to allow experiments to easily scale up? How do you make it easy to have experiments that contain various types of network heterogeneity? For example, maybe different links are dropping or coming up. Different links between clients might be faster or slower, and across the sort of the full gambit. So let me walk through these components bit by bit. So one way that we thought we could make it easy for folks to scale their experiments up would be to have a module that was compatible with existing cloud services, whereby through writing just a very simple configuration script and providing, of course, you have an Amazon or a similar cloud service account, the system could immediately start up a number of instances, perhaps assigning different clients to different threads in those instances, essentially allowing you to get, with a minimal amount of code, the ability to instantiate different types of experimental settings where you could have clients maybe even into the range of 1,000 or even 10,000, depending on what you want to really test and stretch your algorithm to work within. So one key component of Flower is this ability to interface to existing cloud services to do this type of control and establish and tear down the different instances and so on. And we've implemented this to start with Amazon AWS, but we expect to sort of branch this out to different types of cloud providers as a means to get very quick, easy scale in your experiments. You also find in this framework network simulators, whereby you can have your topology of federated learning clients and then highlight which of those, what are the types of link characteristics that you want to simulate. So in the case that you want to have large scalable experiments that are really going to sort of grow beyond your ability to have real actual devices, and you're going to do somewhat of a simulation, you can define different network characteristics you want. You can also estimate the energy consumption very coarsely for those instances, or if you happen to run Flower using real devices, there are hooks there that you can connect this to well-known types of energy monitors like Monsoon to kind of have it spit out for you easy to, basically easily gathered statistics about individual nodes or their collective behavior in terms of energy as well. And finally, there are 3 ways within this framework that you can accommodate and explore the issues of compute heterogeneity, meaning a spectrum of compute capacities within your federated learning clients that you're federating across, as well as memory constraints that may fluctuate both on the actual raw availability of that resource on the device, or if there are second purposes that perhaps the user is doing that might further constrain on the memory available to you. There are 3 ways. First way is the same way that we have hooks into cloud services, where those cloud services like Amazon has device farms. We have additional hooks where you could not just instantiate onto instances that are typical full computers, but you can target actual devices within their device farm, say Android devices and so on. So we want to make it simple for somebody using Flower to target maybe a collection of Android devices that exist within the Amazon cloud service, normally used for testing Android apps under a variety of device types and versions. We want to allow those to be exposed to provide heterogeneity very instantly, people running experiments. Similarly, if you're using just normal instances that exist within these cloud services, we have components that allow you to degrade their computational capacity so that you can simulate different levels of computational capacity across instances that are otherwise homogeneous. And then finally, the most authentic way that you can do this is by implementing different types of Flower clients. And we have a few examples there already. And then you can actually use real devices, set up a system of these devices in your lab and do these tests for real. So really, this whole setup is designed for you to scale your experiments up using these simple configuration DSL that I'm showing you on the right-hand side. So you instantly get up and running in terms of scale. You can run these sensitive analysis of system resources of various kinds, network, wireless, computer memory, and then have a system that allows you to repeatedly compare what you're experimenting with to other types of algorithms that you see in the literature under identical setups to provide systematic, repeatable types of experiments that you can then report on in a way that doesn't force you to jump through many other additional hoops, which otherwise leads people to really only evaluate under a sort of narrow part of the design space. And finally, something that might not be immediately obvious is that although I've talked a lot about Flower's capacity to provide sort of experimental apparatus for doing different types of evaluation, it's also able to run different types of federated learning systems that you want to perhaps launch, particularly if you want to explore different types of basically the application design space that goes on top of federated learning systems. If you want to launch those and test them, Flower is also able to offer that type of functionality and run an actual system. So before I move on now into showing you some sort of early results that we've gathered using Flower that we hope that folks can look at and then build on top of. I just wanted to show you a few screenshots of the code and just how simple and easy it is to get up and running with it. We like to say that we're trying to build a system where somebody can build a federated learning system with even just a single line of code. And that's what's being shown with line 2. The other two things that are really important to us is to build a tool that is, as I mentioned before, very easy to integrate with existing code. Folks obviously spend a lot of time building centralized models, perfecting them, making sure that they're going to behave nicely under a variety of different data distributions. So what they can do is reuse all of that code and write code that you're seeing here in number 1, where it's simply just data marshalling code in and out of their framework and into Flower. Is all they need to do. And often, obviously, for the common frameworks, we already have these written for you. And finally, 3, making it simple to extend the functionality of existing algorithms or write from scratch your own and just plug it straight into the framework and have it tell you how good your idea is. So let's look at, I think it's 3 different types of results we've generated so far with this framework, where really the emphasis has been in building a tool rather than generating the results that we think the tool is capable of producing. These first 2 experiments are really talking about the scalability. They were meant to provide you with initial evidence to convince you that it can scale and it's stable. So if we look at the first plot on our left, this was a really interesting experiment because we ran Flower at a fairly large scale using Amazon instances for over 2 weeks. And we did that because we wanted to show and also show and see the results of using Flower to train ImageNet. So I've not seen very many results in the literature of federated learning where people actually evaluate their federated learning algorithms on ImageNet scale data sets. This happens to be a ResNet 18, and before we sort of start to see the accuracies plateau in the system, it took around 2 weeks of the framework being up and live in those instances, exchanging gradients. And so you can see that it reaches fairly good accuracy, given when you allow for the fact there's a long tail of quite technical issues still left to be resolved as to how do you want to train complex data sets and in architectures under federated learning systems, which of course we have not addressed. We have just experimented with the current set of options for doing things like batch norm and so on. So obviously the accuracies are not quite there yet. So that's result number 1. The result I want to show you also here on the on the right-hand side is a different type of scalability, not about stability over multiple weeks and training what are very complex data sets, but on scaling in terms of the number of clients. So again, using Amazon as a sort of the availability of for availability of instances that we can hit. We show here the behavior of Flower as it's training ResNet 18 under the CIFAR 10 data set under various number of clients, ranging from 10 to 50 to 100, all the way up to 1,000. And the point here is that we could do this just by changing one line in the configuration script, where we just changed the number of clients from 10 up to 1,000. So you can. So I think this should be a really eye-opening thing for folks who want to evaluate their new algorithmic idea under this framework. They can easily scale. The next two results I wanted to show you are very preliminary, and I think to people who have spent a lot of time with federated learning, perhaps they will not be that surprising. But what we wanted to do was use Flower to just see how bad are some of the issues to do with compute and network heterogeneity within our federated learning clients. So these two results here are looking at issues to do with computer network diversity within your system, and asking questions such as, what is the impact going to be on training time? So if we start off with the figure on the left-hand side, we have a new data set that is fashion MNIST, and the experiment here is on an architecture of ResNet 50. The main thing I want to draw attention to is that we have identical setups being plotted with red bars and blue bars, where I think there was around 50 clients, with 5 clients being picked each round. But the difference between the red bar and the blue bar, because it's otherwise the same, otherwise identical setups, is the training time that you get with fashion MNIST when you have just one of the clients suddenly has their GPU disabled. And so if you have one client much slower than the others, whereby they have to do their training on the CPU, so they're going to be slower. Every other client is exactly the same as before, using an off-the-shelf setup. You see that leads to dramatic increases in training time. And so then this is a factor that Flower can assess for you. There's a sensitivity that Flower can immediately assess for you, given the type of algorithm you're evaluating, because it's likely to happen in a realistic situation. And the point here is that this type of heterogeneity can be appreciative. If you're not measuring for it, you might overlook it in terms of the impact on the algorithm you're designing. And it's appreciable, and it's very easily accessed using the Flower framework. Let me move now to a different type of heterogeneity, one where you might have different types of network speed. The question is, what happens if I'm building an algorithm and I'm not testing its sensitivity to the speed of the network connections between my federated learning clients? You might, even if you're doing a real world experiment, you go to all the effort of taking a bunch of devices, I don't know, getting the training loops and everything to run directly on them. You've spent a lot of weeks of work. But then you connect them using a wide connection that's stable, perfect, always consistent. Well, this sort of experiment will show you that you're going to be missing out on appreciable types of behavior. So if you do have wide connections that are nice and beautiful, you're going to have speeds such as this gigabit speed here on your far left, the first bar that you see. But if you, whenever that system has a slowdown in terms of network connectivity, which is something quite reasonable. For example, you might have the same system and suddenly they're connected by, say, 4G connection. Under that 4G connection, you would not get 1,000 megabits per second, you get something more like 30. So the question is, what happens to training time? Well, if we take CIFAR 10 as a data set and we see how much longer it takes to train, you're going to see a factor of 2.1x lifting. Again, this is something that Flower can do very easily, and so all you need to do is plug in your algorithm, and then you can start to see how well it holds up under this setting. And the final type of result I wanted to show you along these lines
So sorry, can
is...
I have one question, please? For the
Yeah,
previous
sure.
slide, the
Yeah.
previous graph. Yeah, so you showed, if you go one, this fashionist. So
Oh, yeah,
there you
okay,
have, so once you increase the number of local epochs, it's kind of strange to me that the actual training time increases. So first, like, clarification question would be like, what is the training time? Is it like predefined number of epochs, or is it the time to reach given accuracy?
I think it's a predefined number of epochs. That's a good question. I think it would be a predefined number of epochs, but I have to double check on that.
Yeah, because then, if this is what I was thinking, but then like running more local epochs should actually speed up your training time, right? Because you save on the compute, and you come.
What if you have? But I think
Nice.
what might be happening here is a straggler node, right? You have one node. So in the blue bar, training times has this big jump, and I think it's because the one node has only the CPU, so that although it might be training more locally, it's going to hold all the other ones up.
Yeah. So, but here I meant like let's just focus on the red ones. So why is that the case that when you increase number of local epochs that you run, you actually you get a slowdown? Because in the end you come if you said, if it's the case that you train for a given number of epochs, you have a same computational requirements, but the actual communication decreases. So actually I would expect that having more local epochs would decrease the training time. So that's something that kind of I don't understand from this graph.
So I don't have the answer for that. It's a good question. I have to come back to you on that. Yeah.
Thank you.
Interesting. Yeah, sure. It's a good question. Let me get back to where it was. I think it was here. How are we doing for time? Okay, I better hurry up a little bit. So then this final result of this type is really looking at how many of these factors can also be data set dependent, I think. So depending on how much local compute you're doing, this is as denoted with this E value here. As you decrease the amount of local compute happening in your test setup, you can have severe degradations in the resulting model quality that you end up training. And then this is not always consistent. If you look at Fashion MNIST, you might have a big factor, but if you look at Sapphire 10, it's not so much of a factor at all. And so that's just really kind of just illustrating how these types of relationships also are often data set dependent, task dependent as well. Let me just move a little bit faster to get to the next part of this talk. Okay, yeah. So then I wanted to very briefly show some results that speak to this issue of carbon footprint. Obviously, many of us will be aware that in the world of centralized training, there's many examples whereby things have really gotten a bit out of hand. Large-scale NLP models, for example, are obviously burning far too much energy for the types of results that we're seeing. You might have a model trained that could take produce as much carbon as a whole family of 3 in the US for a whole year in terms of different types of results that are being seen. And so what we wanted to do was, once Flower was able to produce very accurate and authentic statistics about the types of behavior you would see under real world situations of federated learning, we wanted to extend this one step further by seeing what would happen if we overlay some additional types of analysis that would allow us to translate this into carbon, so that we could have sort of an early preview of what are the impact of methods of this kind. And so to do this, obviously you need Flower for the initial behavior of the algorithms and so on. So that's what point number 3 is. But on top of Flower, we had to build up some analysis that would allow us to estimate under some, this type of analysis is always going to be very sensitive to the assumptions you make. And so there are 2 main factors I wanted to point out in this translation from compute and other types of compute resources into eventual carbon footprint. One is country, so where the different locations of the different compute entities are, in both in terms of, it doesn't matter if you're comparing data centers or looking at federated learning clients, that is also going to be an important factor. So we built that into the model that does the carbon translation as well. And also when you're doing comparisons between federated learning and data centers, because we felt that we wanted to provide not only analysis about the types of carbon emissions you'll get from federated learning setups of various kinds, but also we want to provide a frame of reference, right? So that logical frame of reference would be data centers. And when you start to do those types of comparisons, the thing that really jumps out to you is the need of cooling within the data center for the GPUs that are being used, which is not necessarily present in federated learning configurations, because it's a collection of devices that don't need to have an independent source of power for its cooling. The additional cost that federated learning will face that data centers may not is the connectivity between the devices in the wild using wide area networks can contribute quite a bit to the carbon potentially, because a lot more data has to be sent over wide area networks, which can also need to be powered and so forth. So we do allow for that factor in our model as well. So the details, should check out the archive paper that was in the prior slide. But I want to give you just a flavor of what is behind the results that I'll show you next. And so I wanted to show you one preliminary result that is illustrative of the type of analysis that can do now with Flower in this direction. Let me explain the setup for you. Here we are going to train a ResNet 18 architecture. We're going to stop at the 60% accuracy level, and we are going to compare a network of fairly highly provisioned federated learning systems. Each of these clients are going to be NVIDIA Jetson Xavier NXs, so they're relatively very powerful embedded GPUs. You could find them on robots, you could find them in very high-end smart cameras, and they're 1000%, they are going to be representative of where hardware on the edge is going to in the future. So we feel pretty confident about using them as a first example of things. But of course, the mileage will vary greatly if you're trying to do this similar experiment on much more constrained processes. But anyway, so this is an experiment where we have fairly high-end federated learning setup. We're training a relatively complicated model using targeting Sapphire 10, I believe. Yeah, Sapphire 10. And we're going to compare the performance of this federated learning system against a centralized data center situation where you have just a single NVIDIA V100 sitting in a data center doing the same task. And then the question is, comparing these two setups, how do they compare in terms of carbon? And so let me, if I hit one slide, we can focus, let's just focus on the table on the left-hand side. We are comparing you're seeing the numbers you see in the cells of the table are the carbon emissions from performing this operation from different countries. And then the overall takeaway, though, is that the federated learning clients, that training in a centralized manner will cost you around 1.7 times the carbon for this particular setup, which I think is a very interesting result. As we start to sort of unpack this, that's what the figure on the right-hand side is really doing. As we unpack this number, for example, if we look at the numbers related to the US, the right-hand side allows us to see, well, what was behind these numbers. So this figure on the right shows you the carbon emissions that are being produced per epoch or round, depending if you're in federated or data center situations, where the data center line is in red, the federated learning situations in blue, and you'll see immediately that the gradient for federated learning, the amount of carbon produced per epoch is a lot flatter than the V100 case. And that is at the heart of why federated learning is able to produce the model at a lower carbon footprint. Of course, it's not winning in terms of time and latency, because if we look at how long it takes for it to reach its result, it's much, much longer, 8 versus 2. But because the gradient of its production of carbon footprint is so much flatter, it's still able to win. And so essentially, we think this is a very interesting way to study this direction of algorithms, right? Because federated learning thus far is sort of only really starting to be evaluated, I think, in realistic settings, and at least systematically in literature. And then by adding on this new type of metric, that of carbon, it really brings together a variety of different types of systems costs that are hard to access unless you have sort of authentic emulation or ability to evaluate under real system conditions, and then have an additional overlay sort of estimation of what the carbon footprint can do. But then this, I think, also acts as a really nice case study of why we need things like Flower, so we can do these sort of unconventional types of evaluation to really judge how our algorithms are going to behave in the world, not just in terms of end accuracy for some application, but in terms of what societal types of impact that are so important, such as the environment. And so I really want to leave time for questions. So for that reason, I just want to present these two main results, and then open the floor to questions. So again, thanks for the opportunity to talk to you all today. It's lovely to talk in a focused community where I can really just dive into a couple of things we think are going to be interesting and value to folks out there. So I hope it's been useful for you.
So thank you, Nick, for your excellent talk. Yeah. So anybody has some questions or comments? Yeah, if you do so, just please don't hesitate to either raise your hand or put your question to the chat. So I would have like one more general question. So
sure.
About Flower. So what are the next step? What are the things that you would like to implement there?
Well, there are two things. Well, in terms of tooling support, I think branching out to different types of cloud compute, being able to evaluate it at even larger and larger scales. So can we get to an experiment where we can show 1 million clients running at once, and then use that as an example to the community, so that they can actually, what we really want to get to is a place where academics can evaluate their systems at a similar scale that we see companies doing, so then they can really kind of, test out their ideas at the same level and reproduce the things that they see other companies producing. An interesting dimension to this problem is hardware targets. So the Amazon and Google and some other cloud providers can be quite expensive to run these experiments too. But at least now it becomes easy, but it does come at a cost. So then I think something needs to be done community-wide in terms of hardware support, places that we can run these systems without so much cost. Whether it's some sort of, you can imagine a resource of connected, I don't know, sort of mid-tier devices. Maybe there could be a place where there's 1,000 different NVIDIA Jetsons that you could target and run your experiments on. I think hardware is an important part of the take, but not just software.
Okay, so then I would have one other question. So how is Flower maintained? So is it open source? And if, for instance, if I want to contribute, can I do that?
Absolutely. So it's completely open source. I think it's we eventually want to get towards sort of Apache in terms of hosting and so on, and community participation. But right now, if you go to the website, you'll see a list of different features that we want to build out, examples that we want to have. It's important to have replication studies of different types of components done inside it. There's a long laundry list of things to do that we'd love people to pick up on. But we also are trying to do this in-house as well, because we recognize for it to be useful, there's still a long list of things that would be additionally helpful So for example, the latest addition to the team is Pedro, who's starting, I think, he might even start just today. Pedro is next to me on this pictures of series of faces you see. He's joining specifically to try to build out the infrastructure and do federated learning research in general. But no, absolutely, we'd love to have people even just give us feedback in terms of trying to use it and what's not working. I should also add that the originators of this framework, Daniel and Tanner, Daniel did a master's in Oxford recently, and so they're also studying commercial types of exploration of Flower to provide different type of service for folks who are trying to build on it as well. So that I think we hope that Flower can kind of grow in terms of an open source tool.
Yeah, great, thank you. So we have one question from audience. I will try to unmute Igor. So please go ahead and ask.
Yeah, hello, thank you for your talk.
Hi, Igor.
I just wanted to ask you to kind of compare this new framework, the Flower, to TensorFlow Federated. What are kind of the differences, and is it aimed at some different objectives, or it also tries to improve over TensorFlow Federated in some ways?
Well, I don't believe that TensorFlow Federated right now enables you to run directly on the device. So here you can write different clients that perform the different types of training you care about, and then easily federate them together. Flower sits on top, in terms of the design, will sit on top of different types of deep learning frameworks, whereas TensorFlow Federated is integrated inside it. So fundamentally, it's always going to, for example, be very difficult to have different types of frameworks such as PyTorch and TensorFlow and other frameworks working together, as would likely happen in realistic systems. So I think it's the support for real devices, the separation of concerns between training framework and federation service and components, which I think is critical, are two differentiators currently.
Okay, thank you. So maybe then I would have one other question. So
sure.
So is there actually any alternative to Flower that would have at least a similar functionality that you are aware of?
I think there's things like PySift and Leaf. I don't believe they have. I mean, I don't think they have I mean, we're focused on a certain type of functionality that's kind of very. Well, part of this is about realism, scale, and support for the types of devices that we expect to be important participants within federated systems out there. So I don't know of other frameworks that do that. But I think things like Leaf, that has great benchmarking and so on, and PySift are two that come to my mind. Of course, TensorFlow Federated, I expect, will get stronger and stronger. And so we hope that happens too, because it's more about highlighting, I think, a gap in the literature and a gap in terms of community tools. And then I'm trying to fill that initially. But then I think what we really want is it to be filled in some form. And a collection of tools is probably a likely outcome of this.
Thank you. So there is one other question that just popped up. So let me just try to unmute Xie.
Hello.
Please go ahead.
Yeah, thank you for your talk. And I have a question, is that could we use the Flower to run the asynchronous federated at the stage?
Yes. So it's very extensible right now. So if you need to run that type of workload, to be honest, I'm not sure if we support that already out of the box. I think
Yes.
I believe so. But even if it's not supported out of the box, you could easily implement that component, that behavior that you need inside it. So everything is modular and extensible with different APIs. So if that's not possible, you can definitely add it in.
Yeah, I see. Thank you.
Please feel free to contact us about this. We'd love to be able to support this type of behavior or at least and follow the thread of how your experience is in trying to do it. So yeah, please ping us about it.
Thank you.
Okay, Cici, there is one more question from Stefano, so I will try to unmute him. So please go ahead and ask. Okay, so let me read out the questions. Hey Nick, do you use Flavor, or do you see Flavor being deployable to tiny ML systems such as microcontrollers, etc., in the short run?
Oh, short run. It depends what you define by short run. I can tell you that the two things I'm most exciting to see application-wise Flower support is speech and robotics. And so I know that ROS support would be like a really important step, I think, to support that community. And we think the integration shouldn't be too far away. And through people like Titwan, who's involved in this project, we hope to integrate it with SpeechBrain to enable folks to really study speech in a federated setting in the short term. TinyML, I think it depends on how tiny we mean. But I think you probably would, I think TinyML support could evolve quite quickly if we build out sort of a hierarchical styles of federated with perhaps there's participation from other clients that are more powerful to help them along. But I think, you know, A-series, you know, lots of A-series things working together might be a little bit far in terms of 6 months, 9 months from what we plan to do. Stephanos, you're welcome to add it in. I think that'd be great to see it added in.